In the last video, we introduced the concept of the integral, which in some sense is the opposite of the derivative over a certain interval. It basically lets us work backwards, which is ultimately our goal. Because remember, with Newton's equations, Newton's laws of gravity, we're given an acceleration when we solve them, and we want to work backwards and actually get a distance function from that acceleration function. And in order to do that, we have to basically work backwards from the derivative because the derivative could only take us from the displacement to the velocity to the acceleration. So in this video, what I would like to do is kind of build off the concept and the definition of the integral that we introduced last video to actually solve some integrals and see what the solutions to various uh, integrals are for certain functions. So I think to start, we should begin with the simplest function we can imagine, and I'm going to call that, I'm going to call that alpha of t equals c. Now, the reason I'm using alpha here, whereas I used a in previous videos for the acceleration, is because we're also going to use the letter a or the variable a to represent the beginning of the interval. That's common practice. So I want to use a different variable here, the Greek letter alpha, just so nobody gets confused, because things are going to be confusing enough as is. The definition of the integral is pretty complicated. It's even a lot more complicated than the derivative. But just keep that in mind as we're working through problems. So first off, I think we should graph this just to get an idea of what we're looking at. So if we look at A, let me extend this, and let's say this is C here. So this is the value of the function for all points in time. And our question is, okay, what is the value over this interval, A to B? Now, without even using any calculus, without even using any limits or integrals or anything, you should pretty quickly recognize that this is actually a rectangle. Like geometrically, this is just a rectangle. So the area for a rectangle, and remember, the integral can also be interpreted geometrically in the same way that the derivative can be interpreted as the slope of a tangent line at a certain point. The geometrically, the integral can be interpreted as the area under the curve geometrically, and we kind of went into that over the previous video. But if we look at things that way, then the question is, what is this area? And obviously, the area of a rectangle is, I'm not going to use B for base, I'll use L, I guess, because we're already using B to represent the end of the interval. So we'll just call it length times height. So what is the length of this rectangle? So, well, this point is B, this is A, so the length must be B minus A. And what's the height? Well, obviously C, because that's the definition of the function. It's a constant over over all t's. No matter what you plug in for t, the value of the function is C. So the height of this rectangle should be C. So I think this is important because whenever what we're going to do is basically use the definition of the integral to calculate this area under the curve with calculus. But whatever we do, we should get the same answer here. If we don't get the exact same answer, this b minus a times c, then that's a big problem because that basically means that calculus contradicts basic geometry, which should not happen. This should be what pops out when we go through all of our equations. So let's keep that in mind as we're working. Now, what we have here is the velocity over this interval. So basically, it's really the change in the velocity over this interval is equal to the limit as n approaches infinity. Actually, let me start with just the integral, so we get used to this. So it's equal to the integral on the interval from a to b. The larger number is always on top, and we call that alpha of t times the differential delta t, or dt. So this is the definition of the integral, and you ask, I don't know how to calculate this. What does all this new stuff mean? Well, basically, this thing is defined as the following. The limit as n approaches infinity of the Riemann sum. The Riemann sum, by the way, is just it's basically like what we did in previous videos, except we're taking finite sums of these. So we're basically breaking them into a finite number of partitions and just literally calculating what the area is under the curve with our rectangular approximations. The integral is all of these in the limit as you get an infinite number of partitions, or as you move towards that at least. So As you get a really large number of partitions, these approximations, these Riemann sums, actually approximate the integral itself, which is a limit. So if you hear me use the word Riemann sum, that's what I mean by that. And this is basically alpha I star, and remember, I'll explain what the star means again in a second, times delta t. So basically, if you think about it, if we're breaking things up into partitions, so, let's say we're breaking up into 3 partitions, for example, to start. So n equals 3. This distance down here, between basically the length of the partition, is this delta t, and that delta t is obviously equal to, delta t is obviously equal to b minus a over n. It's just the length of the total area divided by the number of partitions we're breaking it into. And the sample point here could really be any point from here to here. It could be any point between this interval. We're just taking some random sample. And the reason it can be any point, if you imagine the number of intervals increasing. So imagine like having a bunch of intervals here. Then the amount of things that you can actually choose decreases. And you're basically forced to choose the actual value of the function as the delta t gets smaller and smaller. So that's what the star means. The star means you can choose any sample point in that partition, as long as it's in that partition. Now for this particular problem, what does that mean? Well, we're actually a little lucky on this one because the function is just a constant. It's a simple constant. The value is the same for everything. So if you take any sample point in any partition, that's just going to be c. Think about it. So let's say this is the third partition, this is the second partition. I guess let me get rid of some of this stuff. So let's go back to our idea of just working with 3 partitions. First partition, second partition, third partition. It doesn't matter what value you choose in the third partition between the right and the right and left points. The value is going to be c because the function doesn't change. So we in this particular case, things are actually easy. We can just substitute in c for that, just the value of the function. And I'm also going to substitute in the definition of delta t. So, that's b minus a over n. So we have that, and now I'm just going to copy the other stuff. I equals 1 to n, limit n approaches infinity. Okay, so what's this? Well, in order to really understand what this is, I think it might be helpful to write out a couple terms. So let me do that now. Let's write out the first couple terms, because remember this whole thing here is really just a sum. It's a sum with n terms in it. So let's just start writing out some of the terms. The first term, c times b minus a over n. Second term, c times b minus a over n. Third term, same thing. The last term is, you guessed it, c times b minus a over n. Every term is the same, and there's really n terms. That's another thing to keep in mind. So we're going from n equals 1 to n, but there is no I here. So if there's no I in this equation, that means this whole thing is a constant, at least with respect to I. It's obviously dependent on c, b, a, and n, the other generalized terms that mean other things, but with respect to I, with respect to the summation, it's actually just a constant. So let me ask you, if you have a constant and add it to itself n times, what does that mean? Well, that's the same thing as taking the term and multiplying by n. That's actually what the definition of multiplication is, if you think about it. So like, for example, 3 times 5, that's the same thing as 3 plus 3 plus 3 plus 3 plus 3. That equals 15, that equals 15. Or you can look at it as 5 plus 5 plus 5. You can look at it as 5 added to itself 3 times, or you can look at it as 3 added to itself 5 times. That's actually what multiplication is. So if we have this constant term added to itself n times, well, that's obviously going to be the term itself times n. And that's actually what this entire summation is going to equal. That's another way to write it. And we want the limit of this as n approaches infinity. Now, obviously, we can't just plug in infinity into this equation. That wouldn't make any sense. But, you can see here, luckily, something jumps out. These two cancel out. So the n in the numerator and the denominator cancel out. So we'll cancel those out. Then we'll plug in infinity, I guess. if you want to think of it that way, and we'll be left with c times b minus a. So that's what we get when we follow the Riemann, when we basically calculate the integral using the definition of the integral for this specific function, the constant function. And you might see that that actually matches what we were using before. This b minus a times c, same thing as c times b minus a. It's just, obviously the commutative property of multiplication. So we can move things around however we want. But yeah, these are actually the same numbers. So that's actually very good. That means that the definition of the integral actually matched what we thought it should be based on the geometry for the simple function that's just a constant. So hopefully that made sense. I know there's a lot of new symbols here and things are somewhat complicated, but we did just use the definition of the integral to calculate an actual number, or at least a generalized equation for a number based on based on the length of the interval and the value of the function. So that is valuable. So let's actually try it now for a slightly more difficult function. So this time we're going to look at basically the second simplest function. We could look at alpha of t, acceleration of t, is equal to constant times t. So this is going to look more like this. This is going to look like that, ct. And our question is, what's this area under the curve between a and b on our interval? So remember that, the area under the curve is sort of the geometric interpretation for the integral. So we're looking for basically this sliver right here, if you want to think of that. Now, you might also notice that you can actually figure this out as well without calculus, because what you can do is you can look at this as basically one triangle minus another triangle. You can look at this triangle, this big triangle right here, find that area, and then you could subtract this small triangle right here, and you'd be left with this area. That's one way to think about it. So if we find the area of a triangle, and if you don't know that, that's 1/2 times length times height. And then in this particular case, the area in the interval is equal to the area of the big triangle minus the area of the small triangle. So that's one way to think about what we're doing. And if we actually calculate that, let's actually calculate that. So let's try to find the area of this big triangle here. I'm just going to trace it out again so you can see this big triangle right here. What's the length of that? Well, obviously this bottom, it's b minus 0. This is coordinate 0, so this whole length is b minus 0, which is b. And then the height is going to be c times b, because that's the value of the function at this spot. So we're going to be left with actually let me move this whole thing over for a second before we go on. So let's move that over a little bit just to make room. Yeah, but we're gonna look at 1/2 times L, which is going to be b, and then times the value of the function at b, which is going to be c times b. C is just the slope of this line, by the way. All right, so we have that, and then a, if we think about a, we're going to have basically the same thing. So let's call that 1/2 times a times c of a. All right, so just doing a little basic rearranging, you can see how this equals c over 2 times b squared minus c over 2 times a squared. Okay, so this is with the basic geometric reasoning, we come up with this equation to represent the area under the curve, which is going to be right here under this function. So that's just some basic geometric reasoning that we did. In the same way that in the last video, in the last problem that we worked, the expression that we get when we use the definition of the integral better match the basic geometry. The same thing better stand here. So that whenever we go through the complicated equation and we get, use the definition of the integral and we go through all these steps, the answer that better pop out at the very end is this. If it doesn't, then we have problems because, again, that would be an example of calculus contradicting geometry, which is not allowed. That means there's a serious problem. So anyway, let's just keep that in mind and actually try to calculate it. So remember, the function that we're doing is alpha of t equals ct. Just graphing that. It's going to look like this. And then we're interested in the area under the curve between a and b. So that's what we're trying to do. And if we use the definition of the integral, we're looking at something like this. So b over a of alpha t dt, and that is equal to the limit as n approaches infinity of the Riemann sum to n of alpha I star, which is just a sample point in the integral, we'll talk about in a second, times delta t. Obviously, delta t equals b over a minus n. So now the question that pops up is, how do we choose this sample point? That's always the hardest thing. Now, in this one, you might remember the previous video, we were just dealing with a constant, so things were pretty simple. We just can plug in the c, because it really doesn't matter what point you choose in any interval. They're all the same. In this equation, with this function, that is not the case. So we actually do need to come up with some way to pick a of I. In order to get an idea of how to do this, I'm actually going to just start by, let's just assume we're dealing with 3 partitions to make it easy. So we have these 3 partitions. We'll call this partition 1, this partition 2, this partition 3. And we want to find, remember this, the star here means we want to find some sample point between this spot. So on the first partition, we can really pick any value of the function here. On the second, we can pick any value of the function between these two. And on the third, we can pick any value here. Now, and actually, let me actually move down this equation just to get some basic logic. Actually, I'll just continue, it's fine. So remember, we're basically trying to find some equation to determine what any of these sample points should be. And you might remember that the distance between these is delta t. The delta t is the length of the partition, because this is the t-axis, this is the alpha axis. So the question is, how do we do that? There are basically 3 ways. So the first way is what's called using right samples. Right samples. That would be like choosing, so for example, A1 in this case would be this. A2 would be this. A3 would be this. You're basically picking the rightmost value on the interval. That's actually the easiest. The second easiest is to do basically what's called the left sample. So, left sample. And that's basically choosing the leftmost value on the interval. So this will be 1, this will be 2, this will be 3. That's also pretty easy. It's a little bit harder than the right sample, actually, believe it or not, and I'll explain why in a second. The third answer is, any sample. Now, you could pick any number between here and here for a of 1, and that would be valid. The problem is you can't really come up with an equation to do that, because it's sort of arbitrary. So there's no way to represent that with an equation, and if you can't come up with an equation, there's no way to really do the math on it, because you can't actually add up an infinite amount of terms. What we have to do is basically use algebra and hope that a simplified expression pops out. That's basically what we're doing now with this definition. This definition is pretty limited, actually. So this one is really, you can't do it. It's not really applicable for that reason. So we got to stick to the right samples. And I already told you that the right sample is actually the easiest to use. So let's just go along with the right sample and see what we can come up with. So assuming the right sample, remember the problem is we're trying to find this. So let's actually just try to actually find it. So what is alpha 1? So that's, alpha 1 star. What is that in this specific problem? Well, the function actually does not matter. As long as we know the function, we know that we can just plug it in to we can always plug some t into the function to get the value at that function. So in this case, we're really trying to just find this point right here. And if we could find this point, we would just plug that into alpha. And then in this case, alpha of t is just c times t, which means we just multiply it by c times that value. But in general, if we could just find this point here for any function and plug it into the alpha function that we already know, that could change based from problem to problem, that would be a solution. So if you just look at it, hopefully the answer is sort of popping out at you. Obviously, this point is a, and this distance is delta t. So it should be a plus delta t. That'll give us this value here, this input value, this t value. And then if we just take that t value, plug it into the alpha function, well, that'll tell us this number, which is the sample that we originally wanted. All right, what about the second one? What about this? What about the right sample for the second partition? Well, it's basically the same story. We're looking for this point. We have the function alpha that we know how to calculate that point based on some input. So we're really looking for this point. Obviously, that's a plus delta t plus delta t. So that's actually alpha times a plus 2 delta t. And then hopefully you notice third one is the same, alpha plus a plus 3 delta t. Because we're trying to find this point, which means we have to find this input. Obviously, that's a plus 3 delta t hops. So that's why that is. So obviously, a of I sample seems like it equals a, or alpha of a plus delta t I. So there we go. We actually do have a function that we can use to find that, which is pretty handy. Now this is now I should emphasize that this is with the right sample. So just let me right above here, right sample. And we actually want to use this. That's the equation we're going to use. If we wanted to find the left sample, this probably makes sense how you could find it. So with the left sample, we would just be looking at a of, so let me go for example, a of n, or let me use I, that's what I used before, and represents the total in this case. So a of I would equal alpha times a plus delta t, same as before, except we're just doing I minus 1 times delta t. Now this should hopefully make sense. So for example, if we're taking the left samples, and this is the first partition, we're not looking at this point anymore. That's the right sample. We would be looking at this sample, the left point. That's obviously just a. So if you plug in, I equals 1, what would you get? You get a of 1 equals delta t times 1 minus 1. This is 0. So this whole thing, that would simplify to 0, and you'd be left with a, which is what we want. It's just the alpha of a. So hopefully you can see how, and then the second partition would be the same way. The second partition, you're just looking for this point. The left, or how should I say this? The right sample of any interval is equal to the left sample of the previous interval, or of the next interval, I should say. So for example, the right sample, this point here is the right sample of partition 1, but it's also the left sample of partition 2. So hopefully that gives you some intuition for why we have this I minus 1 offset when we're trying to calculate the left sample. And this is why I said the left sample, the equation for that is a little bit more complicated. You can see, we'd rather work with just I here than I minus 1. Now this is still usable. You could still plug this in. You could basically plug every spot that I'm going to use this equation in with this, just having this I minus 1, and you'll actually get the same answer. But, why would you do that? Why not just use the simpler one? So that's what we're going to do. This is how we're going to determine the samples. So I'm going to take this whole expression, or I shouldn't do that, but basically I'm going to take this whole expression that I wrote here and rewrite it below, and I'm going to basically substitute this a of I star in here as a way for us to choose our expression. So let me go do that right now. Let's see. So we're looking at v of t equals the limit as n approaches infinity of I equals 1 to n. That's not let me write that a little differently. So the summation there, and then we're gonna just copy this. So alpha of a plus delta t times I times delta t. So, and by the way, our function here, remember, is alpha of t equals c, the constant slope, times t. If we have any function here, so if we have alpha of t equals, you know, x to the, or I should do x, let me do t, do, t to the third 17 plus sine of 3t, we can still use this formulation here. It's just this alpha is going to be different. So anytime we see t in this equation, we're just going to plug in a plus delta t times I. But you can still use this. This is the right sample for any function alpha as long as you know what the function alpha is and how to use it. This is a simple function, obviously, so we're just gonna run with this. We're gonna run with this because that's what we're assuming for this problem. So, what does this mean? What does this term mean? It means any time in here that you see t, you can do pattern matching. So you have the function alpha input t. Instead, anytime you see t over on the right, we're going to plug in this term alpha plus delta t times I. In this particular case, that's just going to be c times a plus delta t times I. Times delta t, of course. We still have this term over here. And now I'm just going to do a little bit of distribution and make a couple more steps. So that's going to be c times a plus c times delta t times I all over delta t. And we'll just distribute again. So c times a times delta t plus c times, I'll say delta t squared this time. Delta t squared times I. There. So this, and remember, we still have all this stuff. So that's the summation here. Okay, so that's what we have here. If we basically apply the sample equation that we found before, just looking at the logic and the geometry of the problem, we basically come up with this expression. So it's an expression of t delta t's, c a delta t. There's a lot of stuff in here. Remember, delta t is just the width of the interval of each partition. So that's going to be b minus a over n. Now we're going to sub in this b minus a over n into delta t just to simplify things. So let's see what we get there. So if we substitute in delta t here, obviously that's going to be c times a times b. And actually, I'm just going to keep the c on the outside. So we're just going to do this for now. So that's obviously going to be ab minus a squared over n. Okay. And I'm going to do the same thing with the c over here. Keep it on the outside just for simplicity. Now we're looking at b minus a over n squared times I. And here's the new expression. And this is all in the summation, so which is all in the limit. Okay, so now here's where things get a little interesting. We're gonna start trying to solve these limits. So or not solve the limits. That's the second step. We're gonna solve the summation. So I'm basically gonna apply this summation to both of these terms separately. You can do that because summation just means adding a bunch of terms, and you can rearrange the terms however you want because addition is commutative and associative. So that's what allows me to substitute these in. So we're still talking about the limit as n approaches infinity of, and I'm going to take this term and basically apply it to both terms separately. So now we're talking about this c times ab minus a squared over n plus, just going to apply it over here, c times b minus a over n squared times I. And that's all in the limit. Okay, so you might recognize this term here. This term is actually a constant again. So if we go up to the first integral that we tried to solve in this video, let's see where that is. Way up here. So yeah, if you remember this, so we had, this constant, there's no I in this equation, and we're basically adding it to itself n times because we're going from 1 to n, and how that's basically repeated multiplication. We can basically substitute that whole term with just the term itself times n. So that's what we're going to do down here. It's the same thing. It's a different constant, obviously, but it's still a constant. There's no I here. So this should actually just substitute, or this should actually just reduce to c times ab minus a squared over n times n. So there's that. And now with this one, we're actually going to try something a little bit more complicated. But if you notice, this whole thing right here is a constant. So we can actually factor this out of the sum. It's basically the reverse distributive property. So if you have c a plus b, that's equal to ca plus cb. So this term, it's just that with this summation we have, n terms. So instead of 2, we have a lot more terms, but we can still pull out constants. So that's what we're going to do now. We're going to pull out this whole term here, which is a constant, and just leave this I. So let me do that. So c times b minus a over n squared. So that whole thing is a constant that we pulled out of the summation, and we just have the summation of I. So the only term that we need to solve now is this summation of I. If we can solve that, then we can basically get rid of the summations and get on with our lives. So how would we do that? What is the sum of I from 1 to n? So basically, if you think about that, what is that? That would be written as the following. That would be basically what we have. I equals 1 to n. That would be like, if you write it out, the summation, that would be 1 plus 2 plus 3 plus dot 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 plus n, all the way up to n. And the question is, what does that equal for any n? Well, if you want to look into this more deeply, I'm not going to go into this in too much depth, but I recommend looking up Gauss counting, it may be series. So if you look at that, that's that has a good that'll probably have a good explanation of what the sum of this term actually is. Long story short, it's equal to this. So if we do this, or yeah, I forgot the I up here. Whoops. Do that. It's equal to n times n plus 1 over 2. That's the summation. This is basically an equation that based on n that you can just plug in into and get the sum of all these terms. The reason it works, I'm not going to go into that here, but just to give you a little bit of background, this guy here named Gauss, his name is Carl Friedrich Gauss. He was another genius mathematician that lived a long time ago, and basically the story goes, it's not known whether this story is actually happened or not, but it's kind of interesting. Basically, Gauss's math teacher gave the whole class this problem. They said, find the sum of the first natural numbers up to 100. So basically, tell me what 1 plus 2 plus 3 plus 4 plus dot 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 plus 100 equals. And the reason she did that is basically to keep the students busy so that she could relax. But Gauss, being the smart guy that he was, even at that young age, came up with a trick and basically realized that this equation is correct. And he basically used this equation to calculate it really fast. And the teacher was kind of mad at him that he got the answer so fast. So that's kind of an interesting story. I don't know if it's true, but that's how the story goes at least. But anyway, we're just going to use this right now. We're just going to blindly accept this fact without proof and just use it up here. So if we do that, let me actually pull this stuff down. See if I can. Right now, yeah, there we go. So just copy it and pull it down here. We're just going to blindly accept that without proof. So let's see what we got here. Actually, let me delete this. Or I guess I'll leave that. Yeah, just forget about this point here. So just using this fact and applying it here, our new equation, and actually I'm going to move all this stuff over too, just so we have as much room as possible, because we might need it. We might actually need it. Yeah, but actually I'll move it up a little as well. Yeah, so there we go. Now hopefully we can get back to the math. So yeah, we're going to just substitute in this equation for this summation formula. And by the way, the summation formulas are known for for the following formulas: for for I squared, and for I to the third. The above the third, then things start to break down. You can sort of derive it, but it's hard. These are sort of the well-known ones. So whenever you're trying to solve integrals, you're really only going to be able to solve it if you can get it reduced into one of these forms. That's just kind of a side note. But anyway, let's just plug that in, and I'm going to distribute the n here. So I'm just going to write that as n squared plus n over 2. So I hope that makes sense. So this term here is equal to this, and based on this known finite series, it's equal to that. So we've basically gotten rid of the series in the equations, which is good. So that's progress. So this is what we're left with now on the right and on the left. I'm actually going to cancel out these n's, so that'll make things a little easier. So c ab minus a squared plus that, and this is all still in the limit. Okay, so that's nice. So we've at least gotten rid of the series. Now we just need to do a bunch of algebra and hope the right thing pops out. So everybody cross their fingers. What should we do here? So obviously we're gonna have to FOIL this. So that's sort of the first thing. So I'm gonna square this n in the denominator and pull it out. So we'll have c times 1 over n squared, and then this b minus a squared is gonna be b squared minus 2ab plus a squared. And then that's all going to be times n squared plus n. And I'm actually, instead of dividing it by 2 there, I'm going to pull the 2 out up in front here. Hopefully you understand that. So 1, 2, 1 half. So I just pulled this half out in front. Or I'm sorry, I must have made a mistake there. That's supposed to be c divided by 2. Okay, so that's a complicated expression. This whole thing here is, you can look at this whole thing as sort of a constant and distribute it into this. That's what we're going to do next. So let's do that. So if I just, or you can look at it the reverse way, that might make more sense. If we put in this n squared and basically distribute that into this whole expression here, that's basically just going to get rid of this guy, because we're going to have an n squared, the numerator and denominator cancel out. So we're going to be left with c over 2 times, b squared minus 2ab plus a squared. Okay, so that's one thing. So we've distributed this guy in, and now we're going to just distribute this guy in. It's basically going to be this exact same term, except we're going to be left with an n in the denominator. So let's do that. So plus 1 over n, c over 2, b squared minus 2ab plus a squared. Alrighty, so that's something. And now we have, c times ab minus a squared plus this whole thing, this gigantic expression. And this is actually relatively easy, by the way. There, if you try to do the next integral for if you try to solve the integral for alpha of t equals t squared, you're gonna wish you were solving this integral. That's even harder than this. So anyway, we're just gonna quit complaining and keep going. So this is the new expression. So we're actually making progress, and if you think about it, a lot of things could simplify. At this point, remember, we only have n in this spot right here, this n right here, and we don't have the n in these terms at all. So now we can actually take the limit of this expression that we've gotten rid, now that we've gotten rid of all the summations. Now, I just want to make a quick note. When we're doing the derivative, for derivative, you basically have something dot 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 over delta t, and you're letting delta t go to 0. Now you can't actually calculate anything divided by 0 if you try to do something like that, right? Let's say you calculated anything divided by 0.0000001, you get like a very large number. You'd basically get infinity. So in the terms of a derivative, we basically want to get rid of the delta t in the denominator. With the integral, though, with the integral, we start with the delta t. We have basically something, the sample points times delta t in the denominator. And this one, we're actually letting, actually I shouldn't say the delta t. I'll actually say basically we start with n in the denominator. N is related to delta t, obviously, on the interval. But we start with n in the numerator here. So like if we go up on the top, you can see even in the previous step, like just looking at the previous step, it looks like you have n in the denominator, or n in the numerator. So n squared plus n. If you tried to take the limit as n approaches infinity here, infinity squared plus infinity, infinity, your answer is nonsense. It's just infinity. But if you get infinity for every answer, obviously that's nonsense. So the integral isn't even useful in that case. So with the integral, we basically want to get the n out of the numerator and get it into the denominator. Because if you get it into the denominator, then think about what happens. What happens if you can't actually plug infinity in here? But what this limit means as n approaches infinity is basically let n get super duper large. So think 10,000, 10 million, 10 trillion, 10 Googles. Look up a Google if you're interested in what that means. But it's basically a really big number. Think about what happens to this whole term if you plug in a gigantic number here. 1 divided by a gigantic number is an incredibly small number that approaches 0. It's very close to 0. It gets closer and closer to 0 the bigger this n gets. So when we say n approaches infinity, and we plug that in here, that really is making this term here 0. And then we have 0 times all this stuff, which really makes this whole thing 0. In other words, taking the limit as n approaches infinity makes this entire term 0. As n gets larger, this term is going to become less and less relevant to our output. So if we just go along with that, we're left with this expression: c times ab minus a squared plus I'll just keep it there for now. C2 b squared minus 2ab plus a squared. Okay, all that stuff. So, and we don't have the limit term with us anymore because we already took the limit as n approached infinity to get rid of this guy. So now we're left with this. It's basically this first term, this whole first term and that whole second term. That's what we're left with. Okay, so this is actually coming together. Now, this is just some complicated expression in terms of a. It's really a function of a, b, and c. A and b being the intervals, remember? So talking, c of t is the slope of this. C is the slope of this line, and we're talking about a and b. So this is a function in terms of only c, b, and a, which is looks promising. That's basically what we want. So in order to solve this, let's see. In order to make the math easier, I'm just going to factor out the c. So I'm going to say c. I'm going to factor it out of this term and this term. And I'm basically going to, so now we're left with basically a, b. Actually, I'll quit grouping them together too now. So ab minus a squared plus 1/2 b squared minus 2ab plus a squared. Actually, let me get rid of it. Or, yeah, I'll actually just make this a regular parentheses. Okay, so we got that. Now let's apply this half to this equation over here. So that's going to be, 1/2 b squared minus, 2 times 1/2 is just going to be ab plus 1/2 a squared. That whole thing, and then obviously we still have ab minus a squared over here. All of this is going to be times c. So if we scroll down a little bit, get a little bit more room, you can see now we're going to see if we can simplify any terms. So we have ab minus ab, so that's convenient. Those cancel out. And then what do we have? We have this b squared, this can't be simplified anymore, but we do have this. This is minus 1 a squared. So we basically are looking at minus 1 a squared plus 1/2 a squared. What does that equal? That equals minus 1/2 a squared. And we're still left with this term. So we're looking at 1/2 b squared. And remember, all this times c. Is this starting to look familiar? So if we plug this in, the answer to this integral for a general a and b and c, you can plug any number you want in for c or a or b, and this equation will basically tell you what it equals. So that's kind of convenient. But basically what we get is c over 2 a squared. So this is the answer for the integral over a general region with a general slope, assuming that the function that we're integrating is of this form with some general slope c. Now, remember at the beginning of the video, we want to make sure that math makes sense, basically. So, because we already know how to calculate this with basic geometry, adding and subtracting the areas of triangles. So let's see if that matches. Let's go back up, all the way up to see where we started. So that's basically this here. I'm going to copy that, and hopefully that matches. And you can see we're talking c over 2 times b squared minus c over 2 times a squared. So that's good. They do match. So good news. Math does make sense after all. So check. It matches what we thought. So yeah, so if you think about what we did in this video, just to do a brief recap, we basically found b over a of c dt, and we found this. All this work we did in this video was really just to integrate these two functions, c and ct. That's all we did. But we did get answers that made sense, and in the next video we're going to think about what those answers might imply, and ideally how we can find a better way to do integrals. Because remember, this process is like a huge pain with a lot of potential mistakes. We really don't want to do this every time. So hopefully we can come up with an easier solution next time.